More than 100 million Kalashnikov-pattern rifles exist today, and the standard explanation for their near-unstoppable reliability is familiar. Loose tolerances let debris pass through. But that phrase confuses two separate engineering decisions. One about how parts are manufactured, the other about how much room they're given to move. Understanding that difference reveals a deliberate compromise most weapons designers of the era refused to make. In the aftermath of the Second World War, the Soviet military faced a massive logistical challenge, rearming a vast, rapidly expanding conscript army of millions. These soldiers, often poorly trained in mechanical maintenance, needed an intermediate cartridge, selective fire weapon, that would function under the worst environmental conditions without constant care. The Soviet Ministry of Arms Production prioritized dependable cycling, durability, and ease of field maintenance over the tight precision manufacturing standards typical of contemporary Western infantry firearms. Mikhail Kalashnikov, a tank sergeant turned designer, led the development team that answered this practical brief. His group recognized that a soldier in a muddy trench valued a rifle that cycled consistently far more than one capable of firing tight match-grade target groupings. Rather than aiming for pinpoint accuracy, Soviet planners accepted wider shot dispersion as a logical design trade-off. This deliberate choice dictated the internal architecture of the new weapon, establishing a baseline where generous operating clearances between moving parts kept the system running even when neglected in the field. The popular phrase loose tolerances conflates two distinct engineering concepts: manufacturing tolerance and operating clearance. Manufacturing tolerance is the allowable variation in a part's physical dimensions during production. Operating clearance is the intentional, functional space left between those parts so they can move freely after assembly. Soviet engineers did not build an imprecise rifle. Key interfaces, such as the locking lugs, chamber dimensions, and barrel rifling, require strict, controlled geometry to keep the weapon safe and operational. However, the non-critical interfaces, like the bolt carrier rails, feature generous operating clearances. This intentional spacing of up to 0.3 of a millimeter ensures the action continues to cycle despite thermal expansion, metal wear, and minor manufacturing variations. The rifle's design prioritizes a defined working space over tight, restrictive fits, ensuring that physical interference does not easily bind the mechanism. In the field, environmental exposure acts as a direct mechanical opponent. Fine dust and airborne grit settle onto sliding metal surfaces, microscopically increasing friction at moving interfaces. When larger sand particles enter the action, they physically block the path of traveling parts, while coarse grit or dried mud can wedge between tight components to halt movement entirely. Internally, rapid heat generates carbon fouling, baking hard deposits around high-temperature areas to reduce the space necessary for free travel. Moisture introduces rust, changing surface textures and driving up sliding resistance. Even the behavior of gun oil changes when contaminated by dirt or exposed to freezing temperatures, transforming liquid lubrication into a thick, binding paste. A single obstructed cycle at the wrong microsecond can cause a stoppage. Even if the rifle's main action retains the power to cycle, parallel systems like the magazine feed lips remain vulnerable to particulate binding, halting weapon function without breaking a single steel component. The mechanical solution to environmental fouling lies in a high-energy, long-stroke gas system. When fired, propellant gas drives an integrated piston and bolt carrier rearward. This combined reciprocating mass weighs over 0.5 kilogram. Because the piston is welded to the carrier, it acts as a heavy ram, generating nearly 5 kilogram-meters per second of momentum to plow through carbon and grit. As the carrier travels, a 45-degree camming slot forces the bolt to rotate and unlock, generating a pulling force of approximately 5 kilonewtons. A sturdy, oversized extractor claw grips the case rim, tearing the spent shell from the chamber. Simple steel parts and chrome-plated surfaces maximize this operating margin. Firearms design specialist Dr. Alexei Petrov explains the logic. People assume loose clearances mean careless manufacturing, but that is a misunderstanding. Tolerances dictate production variations, while clearances are the intentional spaces left between moving parts. Kalashnikov designed wide clearances to let dirt pass, then used a highly energetic gas system to force the action through any remaining resistance. The Soviet military required a manufacturing system that could produce millions of rifles with interchangeable parts across vast supply and repair networks. Early production models, manufactured from 1951 to 1959, relied on a milled receiver machined from a solid steel block. While durable, this design was incredibly labor-intensive and expensive. To streamline production, the Soviet Union adopted the AK-M in 1959, transitioning to a stamped sheet metal receiver. Stamping reduced machining time, saved raw materials, and cut the rifle's weight by a full kilogram, though it introduced new dimensional control challenges. To maintain reliability within this more flexible receiver, engineers intentionally widened the operating clearances. Historian Dr. Peter Van Cleve notes that the 1959 transition was a deliberate industrial strategy where expanded tolerances were mathematically calculated to absorb manufacturing variations. This design variation did not indicate careless workmanship. Rather, it was a highly disciplined factory-scale engineering solution to guarantee consistent function across millions of mass-produced weapons. The transition to the 7.62 by 39 mm cartridge also produced the SKS semi-automatic carbine. Though sharing the same ammunition, the SKS uses a tilting bolt and a short-stroke gas piston within a traditional wood stock. These tighter mechanical interfaces yield a clean condition 100-meter shot group of 7.8 centimeters, compared to the milled AK-47's 9.2 centimeters using standard military ball ammunition. Looking beyond the Soviet inventory, the American M1 Garand, firing .30-06 caliber from a gas-operated rotating bolt, averages 5.5 centimeter groups at 100 meters. But its tight tolerances fail rapidly when exposed to field grit. The Belgian FNFAL battle rifle, chambered in 7.62 by 51 mm NATO, uses a tilting breech block and premium iron sights to achieve 6.0 centimeter groups. Yet it demands highly complex machining and strict manufacturing consistency. A rifle's precision depends on a chain of variables, including barrel rigidity, ammunition quality, trigger weight, and receiver stiffness. The AK's generous clearances allow the receiver to flex and the bolt to settle slightly differently between shots, increasing dispersion. Yet Soviet planners deemed this service accuracy acceptable for a 300-meter combat envelope, where hitting a man-sized target was the priority. As military technology curators point out, designing for loose clearances eliminated the need for specialized hand fitting during assembly. This allowed factories to maintain extreme production speed and part interchangeability, deliberately sacrificing target-grade precision to guarantee that every rifle built would cycle in the mud. Every mechanical system operates within a bounded envelope. The term unstoppable is a marketing description rather than a mechanical reality. The weapon retains a non-zero stoppage rate. In Soviet trials, the rifle averaged 2,800 rounds between malfunctions under dusty conditions. Action failures occur when extreme carbon fouling chokes the gas piston, or when sub-zero temperatures below -40 degrees contract the steel. Corroded locking surfaces, poor maintenance, and out-of-spec ammunition regularly defeat the system, while damaged magazine feed lips remain the leading cause of feeding failures. Original Soviet production standards do not automatically apply to later global copies, which require separate evaluation due to varying manufacturing quality. In 1974, the Soviet military updated this mechanical formula with the AK-74, while this later generation adopted a smaller 5.45 by 39 millimeter cartridge and modified several components. It retained the broader Kalashnikov operating philosophy of wide clearances in a high-energy gas system. This adaptable design allowed the platform to proliferate through licensed and unlicensed production across the globe. Factories in different countries tailored the rifle to local tooling capabilities, using alternative steel grades, stamped or milled receivers, and various cartridges. These derivatives, ranging from the Israeli Galil and Finnish Valmet to the Chinese Type 56, exhibited varying levels of build quality and mechanical tolerances. However, they all preserve the core operating cycle and a distinct family resemblance. The platform's lasting legacy is a direct result of this balanced engineering approach. By combining acceptable battlefield accuracy and robust construction with simple manufacturing requirements, the Kalashnikov system proved that a forgiving mechanical layout could survive diverse production environments and still perform reliably in the field. Ultimately, the Kalashnikov proves a fundamental engineering truth. Mechanical perfection is often the enemy of practical utility. In an era of hyper-complex systems, it remains a masterclass in calculated compromise. Survival belongs not to the most refined design, but to the most forgiving. Share your thoughts in the comments below.